This how-to video will review how to simplify exponents, including product property of exponents, quotient property of exponents, exponents of zero, and then negative exponents. The final 3 slides show examples including all of these rules put together. The product property of exponents shows what can happen if you're multiplying two expressions that have the same base. In this case, the base is both x, and they're being raised to a power. So one way to see this is to use expansion, or to actually write it out as multiplication. So x squared, we know, means to do x times x, and then x cubed means to do x times x times x. So if you actually do out the multiplication, you have x times itself 5 times, which would give you a final answer of x to the 5th. So if you want to expand it out, you're always able to do that, or if you can recognize that when you're multiplying, keep in mind these are being multiplied, the rule says that you're allowed to add the exponents. So the rule that we can put in this box would be x to the m times x to the n. The bases have to be the same. Then you can have x to the new power of m plus n. Keep in mind that these expressions aren't being added, they're being multiplied. The addition is just a shortcut that you're allowed to do because of the multiplication, and that comes from this expansion. The next product property says if you are raising an expression to a power to another power, what that rule would be. So the cube is happening to the x squared. Remember that to cube something means to multiply by its exact self 3 times. So the base in this case is x squared. But then we can take that a step further, and we know that x squared really means x times x. So everywhere I see an x squared, I can write x times x. So now if I look at this entire problem, I have x multiplying itself 6 times, which would give me a final answer of x to the 6th. So if you don't want to use the expansion method, power to a power, you're allowed to multiply the exponents. So over here, that would look like if you have something being raised to a power to another power, your final answer, you're allowed to multiply the powers together. So on this next example, I'm raising ab to the 3rd power, and again, to the 3rd power means multiply by itself 3 times. And the thing that's being multiplied by itself, or a base, is ab. Since the only operation in this problem is multiplication, there's multiplication happening here and then also between the actual a's and b's, and multiplication is commutative, what I can do is rearrange the order so that way all of my a's come first and all of my b's come second. And so now you have a multiplying itself 3 times, that would be a cubed, and b multiplying itself 3 times, that would be b cubed. So my final answer, when I have a product inside parentheses, it will only work if it's a product, it won't work if it's a sum. You're allowed to give the exponent to each of those. And so what that would look like here, if you have a times b to the m, final answer is a to the m, b to the m. And this is actually really similar to when we saw it with radicals. We saw if you had like radical a times b, you were allowed to give them each their own radical. That's the exact same thing that's happening here. You have something to a power, and you're allowed to give them each their own power. The fact that it's multiplication and multiplication is huge. So this slide is going to focus on actually applying some of those product property rules that we just came up with. So here, the first thing that I want to do is cube everything. I want to get rid of my parentheses, because simplify really means to get rid of parentheses. So this exponent of 3 is touching the parentheses. Every item inside the parentheses is being raised to the 3rd power. So first I would do 3 to the 3rd power, which means to do 3 times 3 times 3, which would give me 27. And then I'm also doing x to the 2nd to the 3rd power. And since it's power to a power, I'm allowed to multiply their exponents and get x to the 6th. And then y to the 4th to the 3rd power, power to a power, I can multiply and get y to the 12th. That's my final answer. On the next example, again, I need to get rid of the parentheses, and to do that I need to cube everything inside. So this time I have 4 items, and the first item that's getting cubed is negative 2. And so that would mean to do negative 2 times negative 2 times negative 2, which would be negative 8. X to the 4th to the 3rd is going to be x to the 12th. Y to the 2nd to the 3rd is going to be y to the 6th, and then z to the 3rd. And then my second expression, the 3x to the 5th, y to the 7th, z squared would just come down. And so now I have multiplication is my only operation here, multiplication is my only operation here, and they're being multiplied, so I can multiply in any order that I want. So negative 8 times 3 would be negative 24. X to the 12th times x to the 5th, because they're being multiplied and they have the same base, you're allowed to add the exponents. Also, if you expand this out, you would see that as 12x's multiplying itself, 5x's multiplying itself, which for a total of 17x's. Y to the 6th times y to the 7th would be y to the 13th, and then z to the 3rd times z to the 2nd would be z to the 5th. So the quotient properties of exponents, we can again see by expansion. So here I'm dividing x to the 5th by x to the 3rd. So if I expand that out, x to the 5th really means x times x times x times x times x. And then on the bottom, x to the 3rd would mean x times x times x. Now, since I have a fraction, everywhere I see an x on the bottom and the top, I can cross them out. So that would cancel, that would cancel, that would cancel. Remember, every time you're canceling, you're left with a 1. So I have x squared over 1, which is just x squared. So if you go from the original, which had a power of 3 and a power of 5, again, the bases are the same, and now I have a power of 2, I obtain that by subtracting the exponents. So the rule is a to the m over a to the n equals a to the m minus n. Keep in mind, these two expressions are being divided. They're not being subtracted, but the shortcut says that you're allowed to subtract. On this next example, we're cubing this quotient. And don't forget that, remember, to cube something means to multiply by itself 3 times. And the thing that's getting multiplied by itself is a over b. That should have an a attached to it. And so then if I multiply across for fractions, on the top I have a times a, which is a cubed. On the bottom I have b times b, which is b cubed, so I have a cubed over b cubed. So this rule says that if you have a quotient being raised to a power, you can give each item inside the power. So a over b to the m becomes a to the m over b to the m. And again, we've seen this with radicals. When it was radical a over b, a quotient inside a radical, you were allowed to split and give each their own radical. So this slide will review the quotient properties that we just took a look at. So 9 to the 7th over 9 to the 4th, because they're being divided and they have the same base, you can subtract the exponents. For right now, I'm just going to leave this as an exponent, but that would really mean to do 9 times 9 times 9. X to the 8th over x to the 5th, because of the same base being divided, you could make it x to the 3rd. Also, in both of these cases, if you expand it out, you'd have 9 7s on top, 7 9s on top, 4 9s on bottom. All but 3 of them would cancel, and the remaining would be on the top. 8x's on top, 5x's on bottom, all but 3 of them would cancel, and the remaining would be on top. On the next example, so here we have negative 3 to the 5th over negative 3 to the 2nd. So my base, the item that's being multiplied, is negative 3. And if I apply the subtraction rule, 5 minus 2 would be a power of 3. If I did that out, negative 3 times itself 3 times, because there would be 3 negative signs, my answer would be negative anyway. So I'm just going to make this negative 3 to the 3rd. Those would be the same. Now the reason they're different, because with the parentheses and without, this is saying to multiply negative 3 by itself 3 times. Whereas this one is saying to multiply 3 by itself 3 times. And then when you're done, just make it negative. But no matter what, you can actually see negative 3 times negative 3 is positive 9. Positive 9 times negative 3 is negative 27. 3 times 3 times 3 is 27. You make it negative, so you have the same answer. The reason this one is considered better is because it doesn't have parentheses. On the next example, the base is negative 5, and if you apply the subtraction rule, you'd have it to the 4th power. So that would really mean to do negative 5 times itself 4 times. Since you're going to have 4 negative signs, this is going to come out to a positive answer, so we can just write it as 5 to the 4th. So here I need to get rid of my parentheses by raising everything inside to the exponent of 2. Since it's a quotient, we can do x to the 3rd to the 2nd. If I apply my power to a power rule, I get to multiply and get x to the 6th. Y to the 4th to the 2nd would be y to the 8th. On the next example, I have a fraction. I have 1 over x squared, and then I have a non-fraction. I could make it into 1 by putting it over 1. To multiply fractions, you multiply across. So 1 times x to the 5th is x to the 5th. X squared times 1 is x squared. And now I can apply my subtraction rule because they're being divided. Final answer of x to the 3rd. So exponents of 0, you can see because, okay, so 2 to the 5th, 32. 2 times 2 times 2 times 2 times 2. 2 to the 4th is 16. 2 to the 3rd is 8. 2 to the 2nd is 4. 2 to the 1st is 1. So over here, I'm decreasing my exponents by 1 each time. The next logical exponent would be 0. 32 divided by 2 is 16. Divided by 2 is 8. Divided by 2 is 4. Divided by 2 is, sorry, it should have been a 2. 2 to the 1st is 2. Divided by 2 is 1. But that's just a pattern. The way that we can actually prove this is we know that, we already proved that if you have x to the m times x to the n, you're allowed to add the exponents. So let's say I had x to the 3rd, and I want to multiply by a number and get back x to the 3rd. Well, we know that anything times 1 is itself. So x to the 3rd times 1 would be x to the 3rd. But then let's write that as, instead of writing 1, let's write it as x to some missing power. Now this rule tells me that since I have the same base, which I do, they're both x's, I'm allowed to add the exponents. So this would become x to the 3 plus whatever goes in that missing box. It's a plus sign. And let's say I want to get a final answer of x to the 3rd. So I need to pick a number in the box, so that way when I add it to 3, I get 3. The only number that can go in the box is 0, which means that x to the 0 and 1 must be equivalent. But 2 to the 0 and 1 were also equivalent. The bottom line is that anything to the 0 power is 1, as long as that anything isn't 0. So here, x to the 0 power, 1. 490 to the 0 power, 1. Negative 2 to the 0 power, 1. Doesn't matter that it's a negative 2, it's to the 0 power, it's 1. Now that would be slightly different than if you had negative 2 to the 0, because this is saying do 2 to the 0 first, which is 1, and then make it negative, so this final answer would actually be negative 1. So negative exponents. We'll look at a pattern again. So 2 to the 3rd is 8. 2 to the 2nd is 4. 2 to the 1st is 2. 2 to the 0 we just learned is 1. So again, the exponents are decreasing by 1. The next logical exponent would be negative 1. 8 divided by 2 is 4. Divided by 2 is 1. Divided by 2 is, we're going to write it as a fraction, 1/2. So then let's divide by 2 again. So 1/2 divided by 2, I could make that into 1/2 times the reciprocal, which would be 1/4. And I want to take this one step further. I want to write it as 1 over 2 to some power. 1 over 2 to some power. So since it's just 2 here, then that power would be 2 to the 1st. Since it's a 4 here, to make that a 4, it would need to be 2 to the 2nd. So I have 1 over 2 to the 1st, just to write it more cleanly, 1 over 2 to the 2nd, to write it more cleanly. So the negative exponent became positive when I made it into a fraction. Negative exponent became positive when I made it into a fraction. So the rule is going to be that if you have anything to a negative power, you make that power positive by making it into a fraction and moving it to the denominator. This would also work if a to the m is already in the denominator, it would move up. So like that would look like if you had 1 over a to the negative m, to make it positive, I move it to the numerator, and then the power becomes positive. The way to visualize this is to use expansion. So x to the 3rd means to do x times x times x, and x to the 5th means to do x times x times x times x times x. So I can still cancel. So on the top, my numerator, I'm left with a 1, because every time you cancel, you're left with 1. And in my denominator, I'm left with x to the 2nd. So there were more x's on the bottom. There were 5. On the top, there were only 3. So after the canceling, the 2 remaining would be on the bottom. Now we also know that the subtraction rule, when you're dividing in the same base, don't forget that you can subtract the exponents. So then this would be x to the negative 2, because 3 minus 5 is negative 2. So you can see that x to the negative 2, by subtraction rule, is actually equivalent to 1 over x squared. So that's kind of why that works. The easy way to think about it, if something has a negative exponent, bump it to the bottom. When you bump it to the bottom, it becomes a positive exponent. If it's already on the bottom, like here, bump it to the top, and it when you bump it, it becomes a positive exponent. So if something has a negative exponent, it moves its location. It just shifts where it is, and that's what makes it positive. So 4 to the negative 2 would become 1 over 4 to the second, which would be 1 over 16. X to the negative 7 would be 1 over x to the 7th. Y to the 7th times y to the negative 12th. Since they're being multiplied and they have the same base, I can use the addition rule. I can add the exponents. They're multiplied and have the same base. So that would be y to the negative 5th. But then because it's y to the negative 5th, that becomes 1 over y to the 5th. By moving the y to the bottom, that's what makes the exponent positive. So on this next example, I'm going to first get rid of the parentheses by raising everything to the third power. So 2 to the third power would be 8, 2 times 2 times 2. X is being raised to the third power. And then y to the negative 5th is being raised to the third power, but since it's power to a power, I can multiply the exponents. So I have 3 items, 8x and y. And they stay if they have positive exponents, they move if they have negative. So 8 and x to the third aren't going anywhere. They're going to stay on the top of my fraction. And since y has a negative exponent, I need to move it to the bottom, and when I move it to the bottom, its exponent becomes positive. The next example, I'm going to raise all 3 items to the third power. So 3 to the third again is 27, 3 times 3 times 3. X to the negative 2 to the third, multiply the exponents, you get x to the negative 6th, and then y to the 2 to the third, you get y to the 6th. 27 and y both have a positive exponent, so they're going to stay on the top. X to the negative 6, it gets bumped down because that's how we're going to make its exponent positive. There are 2 ways to approach this one. So the first thing is, since you have the same base, you have a base of 5, and both are being raised to exponents, you're allowed to apply your subtraction rule. So I could do 5 to the negative 1 minus 2, which would be 5 to the negative 3. Can't leave exponents as negative. It would be like leaving an unsimplified fraction. So since 5 has a negative exponent, it gets bumped to the bottom and becomes 1 over 5 to the third. By moving it down, that's what makes its exponent positive. 5 times 5 times 5 is 125. Another way to have thought about this is you already have a fraction. The 5 on the bottom has a positive exponent, so he's not going anywhere. He's going to stay. The 5 on the top has a negative exponent, so he has to get bumped down. So when we bump down that 5, his exponent becomes positive, and a 1 would take the place on the top. So then obviously we just have a 1 for our numerator. 5 to the second times 5 to the first. Because they're being multiplied, you're allowed to add the exponents. Same final answer. On the next example, I'm going to first get rid of the parentheses by raising everything to the power. Now I don't know actually how to raise something to a negative power, so I'm just going to show that I'm doing it. 2 to the negative 2, 3 to the negative 2. Since they each have a negative exponent, 2 is on the top, it's going to go to the bottom of the fraction. When I bring it down, its exponent becomes positive. Since 3 also has a negative exponent and it's in the denominator, to make it positive, I move it to the numerator. And when doing that, its exponent becomes positive. Final answer of 9 over 4. So the first thing I'm going to do on this example is get rid of the parentheses by raising the items inside to the negative 2 power. So I have 2 to the negative 2, x to the negative 2. Everything else just comes down exactly where it is. So now I have 6 items. I have a 2, an x, a y, a negative 4, an x, and a y. And the next thing I want to do is make any negative exponents positive. So since this 2 has a negative exponent, to make his exponent positive, he's going to go to the bottom of my fraction. So that 2 is going to come down, and that will make it a positive 2. So I've done that. X also has a negative exponent, so to make it positive, I'm going to move it to the bottom, and that would make its exponent positive. This y has a positive exponent, so it's going to stay where it is. Y to the 5th. X squared and y squared both have positive exponents, so they're also going to stay where they are. So then let's talk about negative 4. While negative 4 is a negative number, negative 4 actually has an exponent of 1. Even though the number is negative, the exponent of negative 4 is positive, so negative 4 is not going anywhere, so it stays on the bottom. Now I can start to simplify. 2 squared is 4. 4 times negative 4 is going to be negative 16. Y to the 5th divided by y to the 2nd is going to be y to the 3rd. And the reason those are on top is if you apply your subtraction rule, 5 minus 2 is just 3. You assume that it's in the numerator, or there are 5 y's on top, 2 y's on bottom. When you cancel, there's going to be 3 y's left over, and those leftovers will be on top. X to the second times x to the second, x to the fourth. That's that final answer. On the next example, I have a 4, an x, a y, an 8, an x, and a y. So the first thing I want to do is, if there are any negative exponents, which there are, I want to make it positive. So everything is going to stay where it is, except for x to the negative 2, which goes to the bottom, and when it goes, it becomes x to the positive 2. Now I can start to simplify. So y to the fourth over y to the sixth. There's 4 y's on top, 6 y's on bottom. After you cancel, there's going to be 2 y's left, and those 2 y's are going to be located on the bottom. Also, if you apply the subtraction rule, you'd have y to the negative 2, but because it's negative, that means it goes to the bottom. X times x squared is x to the third. And then I have this 4 over 8, which if that's all you look at, if you look at it as 4 over 8, that's a fraction that needs to be reduced. 4 can cancel and become a 1, 8 can cancel and become a 2. So since everything canceled out on the top, I'm left with just a 1 as a placeholder. 1 over 2x cubed y to the second.